VLSos here. This is a video lesson on arithmetic sequences. We're also going to talk about series. I'm going to start with an equation, function notation, to generate the values of a series. T of n is equal to 50 plus 3 times n minus 1. With it, we can make a table where we choose values of n and use the equation to find the value of the term at that position n. N is the position number in the sequence. T sub n stands for the value of the nth term. So n can't be any real number. N are whole numbers. And the set of whole numbers are positive integers and 0. So we have an initial value of n. It's the position of the initial term. Typically, the first value of n that is used is 0. But in most textbooks that begin with sequences and series have chosen 1 to be the first value of n. So that's the choice we'll make here. If I put 1 into this equation, I'll get 1 minus 1 is 0, times 3 is 0, and then if we add 50, we get the value of the initial term, or the value of the term at position 1, or t sub 1. And we can increase the position numbers by 1 each time and find the value of the term at that position by using the equation. If I put 2 in for n, 2 minus 1 is 1, times 3 is 3, plus 50 is 53. And I can continue to do this. If I put 3 in for n, I'll get 56, and then 59. The sequence are these values, and they're in a particular order, starting with 50. We can see that to get the next term value, we add 3. We add 3 each time. And because the rule to get the next term involves a constant difference, meaning we add or subtract the same thing each time, in this case we add 3, then that's what it means for this sequence to be arithmetic. The arithmetic sequence is this ordered list of numbers that continues as n increases. So what's a series? We're going to make one small but significant change to this ordered list of numbers and turn it into a series. We still have the same sequence in the same order, and this continues, but instead of commas in between the term values to separate them, make them a list, we're going to put addition. And in doing so, we've turned the sequence into a series. A series is the sum of a sequence. A simple change. And just like a sequence where we can observe rules and have notation and symbols for values in certain positions, we can do the same thing with a series with the addition of thinking of a series as a sum of terms as well. In this case, we could use the notation t sub 1, the value of the first or initial term, is 50. We could use the notation t sub 3, which would be the value of the term in the third position. It's in our table, it's 56. The series also has term values. Individual terms can be listed and notated the same way. But we also have sums. So if I use a capital S and put a 1 here, It's very similar to the notation for term values, but what I'm asking with the S is the value of all of the terms added together up to and including the number that I put with the S. So S sub 1 stands for the value of all the terms starting from the initial term up to 1 and add it all together. But with a 1 here, there's only one term to add, so its value is 50. S sub 2 is the terms from the initial up to the second term, and all of them added together. In this case, that's quite simply 50 plus 53. In this case, S sub 2 is 103. S sub 3 stands for the value of the series, meaning the addition of all the terms from the initial up to the third. The third term is 56, so S sub 3 stands for all of the terms added together up to 56. 50 plus 53 plus 56 is 159. So in general, the notation S sub n stands for the sum of all terms from 1 to n. S, capital S, stands for sum. Let's give an example. This is a series. I can see that there are term values in a very particular order, and it appears to follow a rule or a pattern. But because I'm adding those term values together, shown by the addition, then I can call this a series. What I'm going to do is I'm going to identify what we could call this, and I've already talked about it. I'm also going to find T sub n, which would be the rule for the series thought of as a sequence, and then the value in that sequence of position 20, and then find S sub 5, which would stand for the value of the first 5 terms added together to make a sum. First, how to identify this? It is arithmetic because I can see that the rule is subtract 4 each time. To get the value of a term, I take the previous and subtract 4. That's a constant difference of -4. So this is arithmetic. And because I see addition instead of commas, then it would be more precise to call this a series instead of a sequence. That's what I've been given at the beginning. Because it's arithmetic, it has a constant difference, and I found that to be -4. T sub n then is the rule that would generate the terms of this series. And if I know that the initial term is 12, then I can apply the constant difference n minus 1 number of times to make an equation that will generate each term value at position n. So with this rule or equation, I can use it to find T sub 20, which would be the value of the series, but just the term at position 20. In this case, we have an n value of 20, or 12 minus 4 times 20. 4 times 20 is 80. 12 minus 80 is a -64, which is reasonable. If I kept writing term values and they kept on going down from -4, then by the time I got to position 20, I should expect -64. The last thing I'm going to do is find S sub 5. which is the value of adding, or the sum of all the terms from the initial term all the way up to the fifth term. I'm going to assume that I start with a term number 1 whose value is 12. So I'm going to add 12, 8, 4, 0, and -4. I stop at -4. That's the fifth term of this series. Adding the numbers together that I can see that this 0 isn't going to contribute to the sum. The 4 and the -4 are going to cancel each other out. So the sum of these 5 terms is the 12 and 8 added together to make 20.